Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY212, we are at the lecture number 22 and the topic is the superposition and uncertainty. As we know that in quantum mechanics, particle can exist in the superposition of many states. And we also know that the observables, certain observables of the particle cannot be measured simultaneously with 100% accuracy. In today's lecture, we will see that how uncertainty principle can be deduced from the superposition principle. For this reason, we will take two examples. The first example is the initial square wave, and from these two examples then we will see that how uncertainty principle comes out from the superposition principle. So let's start with the initial square wave problem. In the initial square wave, we consider that one-dimensional free particle at t is equal to 0, that is when there is initial time, the particle exists in this state. So you can see that the wave function is defined at t is equal to 0, and it could be 1 over a under the root when position is less than a by 2, where a is the width of the square where the particle can exist, and then it is 0 elsewhere. So this is the wave function of the particle which is in the square wave form. And now, since we want to know that what are the momentum eigenvalues, so as we have already learned that when you know the state and you want to know the momentum eigenvalues, then what we have to do is to expand this psi, this state function, into the momentum eigenfunctions. So the basis, or we call it the momentum space. So the basis or the kind of unit vectors in which we want to expand this psi. So consider this psi to be the element of the Hilbert space. So it's kind of a vector, and then this Hilbert space is spanned by the eigenfunctions of the momentum. And when we expand this psi in terms of the eigenfunctions of the momentum, then everything will be go to the momentum space, and then we will be able to deduce or to derive the probability of the particle to have some kind of momentum. So let's do this. And the momentum eigenstates, let's first define the momentum eigenstates in which we want to expand our wave function. So we want to expand wave function in the superposition of momentum eigenstates, because there will be a continuum of these eigenstates. You can see over here. So this k represents the wave vector and corresponding to momentum, and this is the plane wave in which we want to expand. Now you can see that there are many in continuum, because k can take any value. So this is the continuum of the momentum eigenstates. So therefore we would like to expand to write it in form of the integral. Since it's a continuum, therefore the integral form of this would be this one. So you can see now that the wave function psi at the initial time for the initial square wave is now expanded into the momentum eigenstates or momentum unit vectors, so to say. And this momentum unit vectors are given here, and this b are the coefficients. We have already seen that these coefficients correspond to the probability of finding the particle in one of the states. Okay, so now what we have done, in order to find out the momentum eigenvalues, we have expanded our initial square wave function in terms of the momentum eigenfunctions. So once we have done the momentum eigenfunction, so the next thing is to find out the b, because from these b's we will be able to calculate the probability, or these are actually the probability. Square of them is actually the probability. So for this reason we have to invert the relation to find out the coefficient b. It's a simple mathematics, and we have already done this. Since b, so what you can do here, multiply this equation from psi star with a phi star and here also phi star on the both sides, and here phi and phi star from this integral will go away with giving you some number, and then you will find the b. So this is a Fourier transform. So what we can do, that invert the relation to find out the coefficient bk, because we are interested in them, because they will give us the probability. So bk will be psi phi k star. Now you can see from the left I have multiplied with the phi k star, and then if you put the value of phi k star, there will be minus sign because of the star here, and 1 over 2 pi was in the definition. So you see now that we have find out the value of bk, that is the coefficient which is coming in the expansion of the momentum eigenstates. So let's calculate this integral, because we want to simplify this. So first of all, we have to define the boundaries for our square wave, because we are dealing with a square wave. So let's see, boundaries are from minus a by 2 to the plus a by 2. So minus infinity and plus infinity will be replaced by these boundaries, and the rest is the same. And then if you calculate this integral, this very simple integral, the Gaussian integral, and then you will get the 2 by k outside, and this is from the upper and lower limit. And once you know that this is equal to the sine of ka by 2 k, so the simple cancellation of factors give you this thing. So we know now the bk, that is the coefficients corresponding to the probability, or the coefficients in the expansion of the momentum eigenstates, are equal to this sine wave. And if you plot this, so you will see that the square wave packet at t is equal to 0 should be like this. So the wave function we were initially having psi x0, as you see these boundaries, minus a by 2 to plus a by 2, and this is the square wave potential. This is the on the x-axis it is the position, and on the y-axis is the wave function. So this is the square wave which we have expanded in the momentum eigenstates, and we have calculated the coefficients corresponding to the probability. So once we have calculated the coefficients, it is not very difficult to calculate the probability density to find out the momentum eigenvalues. You just have to take the square. So in momentum space, the probability density is just the b mod square. So we know b, if we calculate the b mod square, this will be equal to this value. You can easily calculate. You have to just take the square of this thing. Bk is already calculated from these simple mathematics, and then if you take just the square of it, you find out. So this is the probability. B mod square is the probability of having particle in some state with a momentum, or having some momentum. Okay, so this function has its maximum at k is equal to 0. You can see because of the sign that when k we put over here, it is having its maximum. So at k is equal to 0, the probability is maximum, but it's dropped to 0 at these values, because when k by a is equal to 2 is equal to pi, if you put it over here, it drops to 0. So from this we now able to plot, and also now able to know where is the maximum probability of having the momentum eigenstates, and where is the minimum probability or 0 probability. Okay, so if we plot it, so you can see over here that this is a square wave packet at t is equal to 0, and this is the corresponding probability bk, or the coefficients only, and the momentum space. So this is the corresponding momentum eigenstate amplitude. Yeah, so this is bk is also called amplitude, because you know that when you plot this probability, or you can see that it fluctuates, and bk actually gives us the amplitude, but from the amplitude we are able to calculate the probability by just taking square of it. So this is the amplitude. You see at k is equal to 0, it is peaking, it is maximum, and it drops out when you go away from it. Okay, so the probability density, so the most probable value is p is equal to 0, because when momentum is 0, this is the most probable value, and you can see that p's value is h bar k, or 2 pi h bar by a, and the momentum values are never found at these values. Okay, so the most probable value when momentum is 0, that we never found it, is these ones, because these are the values where the peak, where the B goes away, and these are the values when it peaks. And so these are the most probable values, but these are not, these momentum values are never found. So we see that some of the momentum values are most probable, but some of the momentum values are never found. So the interval over which momentum values are most likely to be found, you can see that these are the different intervals. But if we take the interval from delta k, from here to here, from this value to this value as plotted here, delta k 4 by a, so you see in this the probability density is maximum. So it is the region where the particle has a maximum probability to be found out. And the other intervals from like from here 2 pi by a or 4 pi by a, you can see that the height of the peak or the amplitude of the peak is decreasing, so it is less probable to find the value over here. And as you go away, the probability is decreasing. So at the p at here at the center, you can see that it is most probable to find the particle with these momentum eigenvalues. Okay. So if you want to calculate the width of the momentum interval, so the approximate width of the momentum interval is delta k, which is 4 pi by a, and this is calculated from this from the plot. And then delta p, if you want to calculate from the width of the delta k, that is the momentum interval, if you want to calculate the delta p, it will be equal to h bar delta k and 4 pi h bar by a. And now we would also like to calculate the corresponding width of the space interval. And the corresponding width of the space interval, the approximate width of the position interval, is delta x is equal to a. As you know that it is going from minus a by 2 to plus a by 2, so the width is a. So if we combine these two widths, and now you can know that why we are combining them, because these are the two observables. We are measuring the position and the momentum, and if you combine both of them, that is the delta x width and delta p width, you can see that it is approximately equal to the h bar. And this is the actually statement, another statement of the uncertainty principle. So now you have seen that from the superposition principle we have derived the uncertainty principle. So the whole procedure was to first expand our initial square wave into the momentum eigenstates and find out the probability of the momentum values, that which are the values which are most probable and which are the values which are not possible. And then we found out the width where the maximum probability was in terms of the momentum, and then we also found out the width in terms of the position where there was a maximum probability. And when we combined both of them, we have seen that the width of delta x and delta p when multiplied together is equal to h bar. This is not exactly equal because we have done the qualitative analysis and not the quantitative analysis. If you do the quantitative analysis, then you put exactly equal, but when you do the qualitative analysis, so there could be some factors coming here. That's why we put this approximate sign, and you see that this is equal to h bar. So this means that it is not possible to reduce the delta x to and delta p product to 0, which means that it is not possible to measure the position with 100% accuracy and also measure the momentum with 100% accuracy. If you decrease the width of delta p, you increase the width of delta x, and vice versa. So it is the uncertainty principle which tells us that the position and momentum are simultaneously cannot be determined. So you see from here that from the superposition principle we have derived this relation. But this was the first example from which we have derived the uncertainty. We have another example as well, and this is of the chopped beam. You will again see in this example that we will show that the uncertainty principle comes out from the superposition principle. So what is chopped beam? Chopped beam in here is the some kind of particles which are moving, and then you can chop it. I mean, you can, for example, if you have beam of electrons going, so you can just chop it in some interval, and you say that in this interval I want to know how many particles are there, and so this is then construct this this interval actually construct the beam. So here we will talk about the system of n interacting electrons, or you can talk about neutrons or any other particles, but it is customary to talk about the electrons. So we talk about the system of n interacting particles, which could be electrons or neutrons. And then the number of particles in the interval delta x dx is certainly rho dx, where rho is the density, that is the number of electrons per unit length. In this case you can consider as the one dimensional for simplicity. And then this rho is actually n psi mod square dx, because this n is the total number of electron, and psi mod square, as you know, is a probability of finding the electron in this interval. So this will so the number of particles in dx interval can be written like this. Okay. Then the total number of electrons will in the beam will be, as you can imagine, that we have to integrate it, because this is the one small interval. So from here to here, for example, but for the total one we have to integrate over all these intervals. So if we integrate over all these intervals, this rho dx, you just have to put from minus a by 2 to plus a by 2. These are the boundaries chosen to make this a little bit simpler. And then this n goes outside, and psi mod square dx. And this interval, if this integral you calculate, it comes out to be just equal to 1. And then you see this is the number of electrons or number of the particles we could have is equal to psi mod square dx. Okay, so in the chopped beam we want to know the probability for single electron in the interval h bar k. So we would like to find out the number of electrons in some interval, but for this purpose we want to find out the probability for single electron in the interval h bar k and h bar k plus dk. So this is the momentum space interval where we want to find out the probability. So pk, so as we already calculated that the probability is the square of the coefficients bk, which comes from the expansion of the wave function in terms of the momentum eigen functions. So this is from the superposition we have already done in the previous example. And the statement is correct if this statement is correct if the total probability is equal to 1. So remember that we can find the probability of a particle in some interval, but the total probability must be equal to 1. So we say that the total probability is conserved. So for example, in this interval from here to here, so particle can be in this interval, or it can be in this interval, it can be in this interval, but wherever it is, the total probability of finding in this whole region must be equal to 100%, which means equal to 1. So that's why this is the consistency requirement, that whenever you want to calculate the probability, you must require that the probability, the total probability from minus infinity to you can say here from minus infinity to plus infinity, this must be equal to 1. So okay, so now we know what is the probability. So the next thing is to calculate the number of electrons in the interval h bar k, and this interval, that how many electrons we have. So this is equal to rho k dk, or n bk mod square dk. So you know this is the density value we have provided, and this is the interval, the momentum interval, and this was a density we have already checked out. And the total number in the whole beam is, if you want to calculate the total number, so definitely you know that if these are the number of electrons in this interval, so we have to integrate over this density to calculate the total number of electrons. And if you calculate, you have to put the value of rho, this n is constant, it goes out, and bk mod square dk. So we now have to calculate this integral. So to calculate the integral minus infinity to plus infinity bk mod d square, it's very simple. You know the value of bk already. We have calculated sine in terms of sine, and also we have calculated the square of it. So from minus infinity to plus infinity, you just put its value, and then to make it simple, we use this dummy variable, or we make the substitution of variables. So eta is by definition k by 2. If you do this, you know that this integral is equal to this is a Gaussian integral, and it gives you the exactly the value equal to pi, and it gives you the equal to 1. After calculating the total number of electrons, it is interesting to calculate the number of electrons in the interval, this interval. And in this interval, again you can see that the delta n, the number of electrons, we can find out this interval. It's just then the putting the value of bk and calculating. And for this interval, this is from okay, so we have to make this substitution, and it goes from plus pi to minus pi, because you can see the other 2 by a just goes away from here. You can see it in 2 by a in here, and 2 by a in the limits. So that's why after the substitution, which we have already done here, this substitution, eta is equal to ka by 2. If you make this substitution, you will find out this eta variable, and if you put the value of pi after the calculating the integral, you put the value of limit, you will find out this value. So it means that the maximum of number of electrons are found out in this interval. So this is 0.9 out of 1, this is 0.903 of electrons are found out in this interval. So it means that the maximum of the electrons are in this interval. So let the electron have the following. So if we have for electron the following momentum, the immediate state after this measurement will be this state. So as I said, from the second example, we will go towards the uncertainty principle. So if we say that electron could have any momentum, but let's say in the beam the electron had we made the measurement and we found out that this is the momentum of electron. So the immediate state after this measurement that electron is in, so this one the immediate state, because whenever you measure the state of the particle, it will be left into the in that state where you have made the measurement. And after this measurement, now energy of the electron, if you want to find out the energy of electron, this will be equal this value, and the position of the electron is certainly p psi naught square is 1 over 2 pi, and you can see that this 2 pi is constant. It means that the probability for the position of electron is constant. So which means that when the uncertainty in x delta x is infinite, the measurement of the momentum finds the value this one, and delta p is 0. So when it was equally probable, because the density, the probability density here, you see this is constant. So this is constant, which means that it is uniformly probable to find out the electron at anywhere. But when it was uniformly probable to find the electron here, so this delta x was infinity, because you can find the electron anywhere. But then the delta p was 0, because we determined that. We started with that the electron momentum is this one. So this is determined. So when this is determined, so the delta p is 0 then, because you know the p, so delta p is 0. So when delta p is 0, and after measurement of this p, the particle is left in this state, and what we see then, that the probability for the position is constant, and when this is constant, we see that when delta x is infinite, because it is uniformly probable to find out the particle anywhere, then delta p is 0. And again you see that this is the uncertainty principle coming out from the chopped beam, that when delta x was infinity, delta p was 0. If you make the delta p equal to infinity, then and let's do it the other way around. When we say that if you find out the electron at specific position, let's say at x is in the beam, we make the measurement in the beam at specific position, and we say that x is equal to x prime, we have found out the particle. So what is the momentum then? So since we make the position measurement, so particle will be left in this state. This is the eigenfunction for the position operator. And if you expand this into the eigenstates of momentum, now this is the expansion. You know that this is the expansion for the eigenstates of the momentum. We have expanded this delta function over here, and now if we calculate the bk, you again see that this is the phi k star, and this is the final continuum for bk, and easily the corresponding momentum probability will be this one, 2 pi. If you calculate this square of it, you will find the 1 over 2 pi, which is constant. And you see that when we have determined the position of the electron, the momentum probability was constant, that is probable everywhere. So what we say that when delta x was 0, delta p was infinity. So we again have seen that in case of the chopped beam, when we find out that electron is at certain position determined, then the momentum is infinite. The not the momentum, but the delta p is infinite. And when we find the specific value of momentum, we find out the delta x is infinite. We can show the plots of them. For example, over here you can see when k naught it is determined, and this width is so narrow, and we have determined that the bk probability is at the k naught at some particular value, and then you can see that corresponding position is 1 over 2 pi, which is infinite, and this straight line you can see. So all the values are possible. So it means that if you have k naught here, this one, so you can find out value anywhere. So it is uncertain which value will come out, this value or that value or that value. It's uniformly probable. All of the values are possible to come out. But if we do the other way around, if we say that okay, we have determined the position of the particle over here, then what about the momentum? It is uniformly probable. So this is the law of nature, this uncertainty principle, which we have calculated from the superposition principle, that this is the law of nature, that once you find out the value of momentum, the position is uncertain, and when you determine the position, the momentum is uncertain. So in today's lecture, we have done the superposition principle and the uncertainty principle. It's a very important and concept, and technically it's important to know that from the superposition principle we can derive the uncertainty principle. So we have given you I have given you two examples of initial square wave and the chopped beam, and in both cases we have seen in slightly different context, but this very simple calculations, that when you have the initial wave function and you expand it in the momentum eigenstates, and after the expansion you calculate the probability for the momentum eigenvalues, and then you calculate the probability for the position, you find out that delta x multiplied by delta p is approximately equal to h bar. This was if you do it in the initial square wave, or you do it in the case of the momentum eigen or in the chopped beam case. In the both cases we found out that the uncertainty principle does exist. So uncertainty principle is the law of nature, that is the law of quantum mechanics, where we say that the position and the momentum are simultaneously with 100% accuracy not determinable. But on the other hand, there are other variables. For example, the energy and time and the angular momentum components, they are also not simultaneously can be found out. But these are we call the conjugate variables. But the other variables, there is no such thing. For example, in energy and position, it is possible to find them out simultaneously with 100% accuracy. So at least the interesting example and the first and important example is the position and momentum, where we have seen that the uncertainty principle does exist. With this, I thank you all.